like we introduced the concept of resistor in an alternating circuit, we'll further discuss about it and try to introduce the concept of phasors. So what are exactly a phasor or phasor diagram? So in the concept of phasor, what we say, if you try to apply a potential difference across a resistance, there is going to be a current that is going to be produced. We know that the potential difference also varies with time. We also get to know that how the current varies with time. So let's try to understand it more deeply about this concept of applying the voltage source across an resistor and what is the production of current, what exactly is the current that is produced. And let's try to also understand it a little more deeply about the phasor for it, R circuit. R means a resistance in an alternating circuit. Let's try to get on to it. So in our last part, we just introduced as to what exactly is an alternating current. Now we go further into that and try to understand about the generation of alternating current and so on. So we discussed that if I have a alternating source, then that alternating source is basically going to produce some kind of a voltage. So if I have to understand about what is the type of voltage, so like we said that you have this, let's say, is the voltage source. The voltage, like the current, is also going to vary with time. The variation is going to be captured by this kind of thing. So either we represent this as F or we represent it by L or by eta. Either of them represent the same thing. So here the variation in the values is basically this. So this is your amplitude of the voltage. So the variation in the voltage goes as in form of the amplitude of the voltage times sine omega t. Omega is nothing but the angular frequency which we have defined, right? So V or delta V is the instantaneous value of voltage at any particular instant of time. Similarly, delta V max or V naught represents the maximum voltage. So it's the maximum value of the voltage that is possible. F is the frequency at which the voltage is basically undergoing the changes and it is measured in hertz. Okay, now if we go further, we talk about the basic principles of AC generation. How exactly can we generate alternating current? So alternating current or alternating voltage is generated by rotating a coil of conducting wire. So let me put it precisely. You just take a coil, okay? You just take a rectangular coil, you rotate it. Once you rotate it such that the magnetic field basically has a particular direction. Once you're rotating it, obviously the flux is changing. So how exactly is the flux changing? So as you're rotating it like this, then the flux is going to depend upon how much is the angle that is being subtended by the area vector, that is this normal, with the magnetic field. So phi is going to be equals to the area vector A dot with the magnetic field B into the normal vector N. Okay, so B into the normal unit vector N into cos omega t. So cos omega t is basically its own value of what is the rate at which it is moving, and theta naught is the original phase difference. The original phase difference between the magnetic field vector and the area vector. Okay, so this is the relation that we get, right? Now here A stands for the area of cross section of the coil. Area we know is basically a scalar quantity. So what we do, if I just say that this is my area vector, so area, how do I represent the direction of it? So for representing the direction, we just take a unit vector or a line coming in the outward direction. So this represents the area vector. This is basically the normal on the area. So this is the area vector that we have. Further, B is the magnetic field. Capital N represents the number of turns. Omega is the angular frequency, which is equal to by F. F is the frequency. Theta naught is the initial phase angle. Okay, so this is broadly speaking the basic principle as to how the AC is generated. So alternating current is generated when the coil rotates. So when the coil rotates in a magnetic field, as a result there is going to be a flux change. So the flux produces an alternating value of current. Okay, going further, let's try to understand how exactly it works. So with the change of time, that is with the passage of time, cos omega t plus theta naught changes, and as a result there is going to be a potential difference V which is produced. So V we know is going to be equals to d phi by dt. This is nothing but the induced EMF that we are aware of when we have studied about the electromagnetic induction. So from the electromagnetic induction, what we know that when there is a change in the flux, so from the change in flux there is an EMF that is induced. So the amount of EMF induced is basically in the opposite direction. The EMF opposes any kind of opposes basically its own production, right? So the EMF that is produced is going to be given by d by dt into AB into the normal unit vector cos omega t plus theta naught. So this represents the value of the potential difference that is produced. Here the amplitude of this is going to be given by this particular factor. So Vm is going to be nothing but AB omega, because voltage is not a directional quantity, so will not be taking into account the normal unit vector, right? Okay. So once we have got to this thing, so what we do now is we now try to find out what is the average value. So how do we find out the average value? So for finding out the average value, what we do, we integrate. So for half cycle, if I have to do it, so you know that the cycle goes from something like this to this. So this is my total time period that I get. Correct? Now for half cycle, effectively you are going to integrate from 0 to t by 2, and t by 2 corresponds to an angle of pi. So effectively you will be integrating from 0 to pi, and here you will get what? I naught into sine. Here you will have 2 pi frequency into the time period dt, and then in the denominator you will be integrating from 0 to pi dt. So once you have this particular result, so obviously in the denominator you will just be getting a factor of pi, in the numerator you are getting a factor of 2 pi, so or 2 pi square or something like that. As a result you will get an expression of 2 by pi. Why do you get something like that? So if I just have to integrate, let me integrate this, that's going to be useful. So I'll get what? I naught comes out, integration of sine gives me cosine, so I'll get cosine 2 pi ft. Further I'll get what? Because I have integrated with respect to time, I'll get in the denominator 2 pi f, and in the denominator here I'll get a factor of pi. Further, if I integrate from 0 to pi, so from 0 to pi, 0 value will give me what? The value of 0 gives me cos 0, which is 1. Cos pi, effectively I need to substitute for the complete thing. So if I substitute for the complete thing, I'll get what? I'll get nothing but, effectively I should be not integrating pi, it should be pi divided by the time period. That should be a proper choice. So pi divided by the time period if I do it, so because I'm integrating over that, so if I do it, so as a result I'll get cos pi and I'll get cos 0, so the difference gives me a factor of 2. So that results into a factor of 2 by pi into I naught. Okay. Time period factor, as you see pi by t, so that cancels out the factor of 2 by f, right? Okay, so this is what we get, and as a result the half cycle, because for the full cycle if I just try to find out that for the full cycle the average value of current is going to be 0, because there is going to be some average value of current here and there is going to be an oppositely directed average value of current. So if I just try to find out for the full cycle, the total average value of current for the full cycle is going to be 0. In the same way if you try to find it out for V average, again it's going to be having a same expression 2 by pi into V naught, right? So this is how the relation goes. As I just mentioned, for the complete cycle, I average is going to be 0. The average value, if I just take it for the whole cycle, that is between 0 to 2 pi, obviously it's going to come out to be 0. It's similar to the case of a standing wave. So there is nothing, there is no energy that is transmitted, so there is no current, no net current that is flowing, right? Okay. RMS value of current. What is RMS? R stands for root, M stands for mean, S stands for square. So root means square value of alternating current is defined as that value. It's a kind of an average value that we define, because alternating current is continuously changing. So you need to find something, an average value. So it is the average value which produces the same kind of an effect. Obviously you define everything in terms of effect. So it produces the same kind of an heating effect in the resistance as the same alternating current that is passed through the resistance, right? That's the reason this is very, very important, because it gives a kind of an analog to the DC. And how do we get to this? We get to this from a simple looking equation. So I RMS square. So this is defined as I naught square, and here you get sine square omega t dt, and here you integrate over dt. So when you integrate over dt, so you integrate from 0 to t. Similarly here you integrate over 0 to t. So once you integrate this, so that gives you a factor of half, right? So this results into something like I naught square divided by 2. So once you get this, you take an average, you take a square root. As a result, you get I RMS, which becomes I naught divided by square root 2. Okay, so I naught divided by square root 2 is nothing but 0.707. This can also be written as 0.707 into I naught. So this is the value of I RMS. Okay, and so is your VRMS. So V naught is nothing but the peak value of EMF. Okay, now we come to the case wherein we define something known as a form factor. Form factor means there is an average value of current that we define. Similarly, we define the RMS value. RMS is a more appropriate value. So how much is the average value different as compared to the RMS value? That is what, that particular ratio is what is defined as the form factor. So form factor is defined as the RMS value divided by the average value. So you get V naught divided by root 2, and the average value is twice V naught divided by pi. So this particular expression is giving you the form factor. So it's nothing but a constant factor. It is irrespective of what is the maximum value of voltage, what is the maximum value of current, it does not matter. It's just a constant for an alternating current. Okay, fine. Let's do an example based on this. So it says, if a domestic appliance draws 2.5 amperes from a 220 volts 60 hertz, the frequency here is equals to 60. The voltage here, so the peak value of voltage is equals to 220 volts, right? The current I naught is equals to 2.5 amperes. So now if we want to find out the average value of current, so I average is going to be equals to twice I naught divided by pi. Average of the square of the current, that is nothing but I RMS. So I RMS is going to be equals to 0.707 into I naught. Current amplitude you already know is 2.5 amperes. Supply amplitude, that is the voltage, that's already given as 220 volts. So it's reading from the question effectively. Okay. Now as I had mentioned in the introduction, that now we will be introducing the different circuit elements into this. So the first element, the first basic element that we introduce is nothing but the resistance. So if we introduce the resistance here, so here we introduce the resistance. So you see that you have a potential difference source, let's say E. So E is nothing but V naught sine omega t. So because of this potential, there is going to be current that's going to be produced. Obviously the current is going to vary with time, but let's figure out how exactly it varies. So if we talk about using the Ohm's law, the resistance follows the Ohm's law, so V equals to I into R. So as a result, you will say E, that's equals to I into R. E is known to you as V naught sine omega t. So you'll get V naught sine omega t, that's equals to I into R. So from here, what you get, I becomes equals to V naught sine omega t divided by R, right? So V naught by R it is. So as a result, this gives you I naught sine omega t. So I becomes equals to I naught sine omega t. So I naught is nothing but the amplitude of the wave. So I is the instantaneous value of current. I naught is the current amplitude that we get. So what is the current amplitude? So I naught becomes equals to V naught divided by R, right? So this is the voltage that is applied across the resistor. Thus the sum of the instantaneous value of current values over one's complete cycle is 0, and the average current is 0. That's obvious, because if you take in for the whole cycle, the total amount of current flowing is going to be 0, and so is going to be the instantaneous value of current. That's also going to be 0. If you talk about for the case of power, so power dissipated is going to be given by I square R. So you can simply say I naught square R sine square omega t. And as a result, if you try to find out the average, so this is going to give you the P average. So P average is going to be equals to I naught square, R can be taken out. It's going to be an average of sine square omega t. Sine square omega t average is nothing but half, so you'll get half I naught square into R. So this can also be simply given by I naught divided by square root 2 whole square into R. So as a result, this gives you I RMS square to R. So that is here. So P bar is nothing but the average value of the current, average value of the power. Yeah. Okay. Moving further, we know that V naught is equals to I naught into R. We know that epsilon is going to be equals to I into R. So if we just write down in terms of voltage, so this becomes V naught sine omega t. In this case, this is going to be equals to I naught sine omega t into R. So if getting rid of the factors of sine omega t, so we get V naught is equals to I naught into R. Now if I divide both sides by a factor of root 2 for basically observable things, that gives me what? V RMS is equals to I RMS into R. Okay, so this is the AC voltage that has been applied to a resistor. Okay, now is the very important thing. This circuit diagram that you see, this graph that you see, is what is known as a phasor diagram. So in the case of if I just talk about the resistance, and here you have a alternating voltage source E. So this is resistance R that I get. So in this particular circuit, which consists of an AC source and a resistor, so in this case the current is going to be here, and let's say this is the value of the voltage that you get. Okay, so voltage V max is basically V naught, I max is nothing but the I naught. Okay, so this is what we get here. Now if I go further, so this graph shows the current through and the voltage across the resistor. The current and the voltage reach their maximum values at the same time, so they are in phase. Okay, current and voltage are in exact phase. So if I just have to plot it, so I'll say V naught is here and the I naught is here. The current and the voltage are said to be in phase, so that is they are going to move together, right? Direction of the current has no effect on the behavior of the resistor. That is, even if you change the direction of the current, because alternating current source it is, so obviously at every instant of time the direction of the current is going to vary. So if the direction of the current varies, so it has no effect on the resistor, because the resistor is neutral to the direction of the current, right? Hopefully you understood till this point. Let's stay tuned for more. In this part, what did we discuss? We discussed about when an alternating current has been applied across a resistance, how exactly is the resistance making the current flow? What is the amplitude or what is the phase difference between the voltage and the current? So we see that there is no phase difference in the case of resistance between the voltage and the current, since both of them are oscillating. When we try to draw the variation of voltage and current on the same scale, we see that there is no phase, so the phasor angle is going to be 0 in this particular case. Now let's try to go further about it in the next part, where we will try to introduce the capacitor and then the inductor, and then we'll also try to understand about the RLC circuit. So stay tuned for that.